All right, so here's a quiz, and it says find the interval of convergence, n equals 0 to infinity, of x plus 4 to the n over 3n minus 1. State the test you're using. All right, so to find the interval of convergence, what's the first test I should use? Yeah, we should definitely use the ratio test. So let's use the ratio test. We should show the work. Don't just say ratio test, but we actually have to do it. So if we're going to do the ratio test, RT, then what we're going to do is we're going to take a limit as n goes to infinity, which that's good enough. You're right. In this class, you're at LIM. That means n goes to infinity. And then what we're going to do is we're going to plug in the n plus 1 term and divide by plugging in the n term or multiply by the reciprocal. So we're going to take x, and it's the absolute value, of course, of x plus 4 to the n plus 1 divided by 3 n plus 1 minus 1. And that's divided by an, but you can multiply it by the reciprocals a lot easier. So we're going to multiply it by x plus 4 to the n over 3n minus 1. All right. So once we've done that, then we're going to kind of put things together and then simplify. So what about x plus 4 to the n plus 1 over x plus 4 to the n? What's that simplify to, that piece? So x plus 4 to the n plus 1 over x plus 4 to the n. What does that become? Yeah, that's just x plus 4. So we get equals limit of the absolute value of x plus 4. And then we have times 3n minus 1 divided by, this becomes 3n plus 3 minus 1, which is 3n plus 2. And now to use L'Hopital's rule, we have the absolute value, still have the x plus 4, and then you get 3 over 3. Which is equal to the absolute value of x plus 4. And then we're doing the ratio test, so we need to set that to be less than 1 to get it to converge. Okay, so in particular, right away, the radius of convergence is 1, but we want the interval of convergence. So we know that the interval of convergence goes from, and now if x is -5, then we get 1, and if x is 3, -3, we get 1. So it goes from -5 to -3. All right, now what we don't know yet are the endpoints. Any questions on that? Okay, so at x equals -5, we plug in. And when we plug in, I'll just write an is equal to, well, -5 plus 4 is -1. So we get -1 to the n over 3n minus 1. Let me stop. Any questions about looking at the left endpoint or anything else I've done here? Okay, now we need to figure out if this series converges. So As I mentioned last week, is that you never use a ratio test for the endpoints. It will never work because you're always going to get one and always going to be test fails. So what test should I use? It's not a hard one. What test should I use to decide if -1 to the n over 3n minus 1 converges? Yeah, we're going to use the alternating series test. So since the limit of 1 over 3n minus 1 is equal to 0, and 1 over 3n minus 1 is decreasing, right? Because as n gets bigger, the denominator gets bigger, which means the numerator gets, the fraction gets smaller. By the alternating series test, what is the conclusion? Yeah, the series converges at x equal -5. Okay, now let's go to x equals -3. Well, if x equals -3, -3 plus 4 is 1. 1 to the n is 1. So that means a sub n is equal to 1 over 3n minus 1. All right, what test should I use to decide if the series 1 over 3n minus 1 converges or diverges? Okay, yeah, limit comparison test. So compare with 1 over n, all right, sum 1 over n, which diverges by the harmonic series test, okay, because that's the series of all examples. So now we take the limit. So we take the limit of 1 over 3n minus 1 divided by 1 over n, or times n. That's equal to the limit of n over 3 minus n. Again, we can use L'Hopital. So that's the limit of 1 over 3, which is 1/3. Okay, and if you remember, unlike the ratio test, with the limit comparison test, what matters is you're not 0 and you're not infinity. You're some finite non-zero number. So we can say by the limit comparison test, the series diverges at x equals -3. So therefore, the interval of convergence is, well, we know that it includes -5. So remember brackets for inclusion, and it does not include -3. So -3, parentheses for not including. So let me stop. Any questions on any of the steps for this particular example? Okay, and you'll notice it's very step by step. Step 1 is use a ratio test to see what the radius of convergence is in the interval other than the endpoints. Step 2 is you look at the left endpoint and use a test that isn't the ratio test. Step 3 is you do the same thing for the right endpoint. And step 4 is you state what the interval of convergence is. Any questions? Okay, if there's no questions, let's do the second one. Second one's quicker. I don't know about easier, but it's definitely quicker. Write down the power series that corresponds to the function f of x equals x to the 6th over 1 plus x. All right. So I want to get the power series for this function. So what do I do to make it look like a geometric series? Because that's all we know how to do so far. That'll change a lot on Wednesday, by the way. So what's the key thing to make this look like a geometric series? Kind of two things. Oh, one thing actually. Yeah, we need to have it as a 1 minus r on the bottom, and you have a 1 plus x. So the way we can do that is we can say f of x is equal to x to the 6th over 1 minus, and what do we have to subtract to make it all work? Yeah, negative x. Any questions so far? Okay, now we can use the geometric series formula. Okay, and the geometric series formula says that if you have a over r to the n, a over 1 minus r, that's always a summation of a times r to the n. So we can write this as a summation. I'll just write sum. And that means going from 0 to infinity, 0 to infinity of, and now we're going to have a, which is x to the 6th, times, and now we're going to have a negative x to the n. Okay, now I'm going to clean this up a bit, which is important to know how to do. So I'll let you know, I probably won't take off points if you don't clean it up on this quiz. But the problem is if you don't know how to clean it up, you won't be able to do what we're doing today. So the new section. So let me show you how to clean this up. The first thing, if I have a negative x to the n, and I want to write as a power series, which means it should be something times x to the n, how can I deal with that negative? Yeah, we can pull out a negative 1 to the n out of it. So I can get a negative 1 to the n times x to the 6th times x to the n. Now I can do a little bit more. And again, I won't take off points on the quiz for this, but you need to know how to do this for what's coming up. So I figured it's worth talking about. So then I'm going to write the summation 0 to infinity, negative 1 to the n. What about x to the 6th times x to the n? How can I write that prettier? Yeah, we can write as x to the n plus 6. So use the power rule for exponents. So n plus 6. And there's my power series. And that's the best way of writing it. Like I said, if you didn't do all the simplification, I won't take off points. But if you don't learn how to do the simplification, you won't be able to do what we're doing today, or next time or the time after. So basically, you need to know how to do this. So I figured it was definitely worth it. Any questions on writing down this power series? Any questions on the quiz as a whole? Okay, if there's no questions, let me ask you about, are there any questions about anything else? Any questions? Give you a second. Okay, if there's no questions, I think we should get to the next section. And that is all about doing stuff with power series. Okay, so all the things that you're used to doing in math. And what's the first thing you learn after learning how to count when you're a child? Maybe 5 years old?
Adding.
Yep, adding. Okay. So we are literally going to start from the beginning. Okay. Okay. So once you learn how to count, then you learn how to add. Subtract comes next, and we'll get there. But the first thing you learn how to do is add. Now, adding two numbers, you better all know how to do that. But we want to be able to add two power series. And the good news is there's no issue. Okay. So let me just do it by example, and then I'll write down the theorem, and then we'll see it. The theorem actually has some nice stuff in it. So let's suppose we have a series n equals 0 to infinity. That one. And let's suppose we have 1 over n squared x minus 2 to the n. And want to add that to another series and copy and paste and change. So you want to add it to n equals 0 to infinity. And let's say you're going to have 1 over n times x minus 2 to the n. So if all things were good in the world, I better make it n equals 1. Otherwise, the whole thing can't work because you can't plug in 0. If all things were good in the world, what would you do? If you could have it your way. Factor out the x minus 2 to the n. That's the second step, actually. What's the first step? Might be so obvious that you're not even thinking that you have to even say it, but actually it is actually very deep, even though it doesn't look deep when you do it. Any thoughts? Okay, I'm not seeing you jump in. Okay, what you can do is, just a minute. Is you can put it all under one sum. Any questions on this? Okay, it might be so obvious you didn't even think about saying it. Yeah, it was a 1, not a 0. Thanks. Yeah, 0's got all kinds of problems because you can't go 1 over n. That's why I made it starting at 1. Okay, you can put it under one sum. And that's really important. It seems obvious, but actually proving that could be done is brutal. So brutal, we're not going to do it in this class. But do you trust me that you can do that? Okay, that if the series converge, then you can put them together. Okay, so that's a big step. Otherwise, you just can't do anything. You're so used to just, rearranging things, but when you have an infinite number of terms, you'd be very careful about what you're allowed to rearrange. So it turns out you are allowed to do this. And then we can do basic algebra. And that is just factor out an x minus 2 to the n. So let's do that. So I can get rid of a bunch of things. And I could write as 1 over 1 n squared plus 1 over n. X minus 2 to the n. Any questions at all on addition? Any questions? Okay. If you felt like it, which you don't have to, but if you felt like it, you can combine, get a common denominator and add them up. But that's not necessary. Any questions on adding these two power series? Okay. For subtraction, I think I'll do the same example of subtraction to let you know nothing's different. Just as an example. So if that plus is a minus, yeah, it still works. I can go minus. And then I can put them together as a minus. And that still works. So addition and subtraction is exactly what you would expect it to be. You just put them together. Any questions at all on addition and subtraction so far? All right, we've spent a lot of time on something with series. And what is that I haven't talked about in this example? Spent like a whole week on it. Yeah, convergence and divergence. So one of the big questions is if you know about the interval of convergence of the first, and you know about the interval of convergence of the second, and you add or subtract, what can you say about the interval of convergence of the sum or the difference? Does that make sense to everyone? That's a big question, a very important question. And the answer is a theorem. So let me show you the theorem. So let's suppose f of x is equal to the summation of a and x to the n. And if I don't put anything here, it's like 0 to infinity or 1 to infinity, whatever the example is. We're always going to infinity on these. And g of x is a summation of bn x to the n. And let's suppose both converge on the interval I. So we found the interval of convergence, and they have the same interval of convergence. Okay. Then the summation of an plus bn x to the n converges to f of x plus g of x on the interval I. Any questions on this the first piece of the theorem? All right, now this is a tough one. Does that mean that if you know the interval of convergence of f and you know the interval of convergence of g, then you know the interval of convergence of f plus g? What do you think? Yeah, what's wrong with saying that why might you not know? Can you think of a very easy example where you don't get the same thing? Bounds included to exclude, that could happen, but it's actually more general. May not even be the same radius. Can you think of an example? Okay, let's suppose, let me give you an example so I don't see y'all jumping in. Let's suppose f of x is equal to the summation n equals 0 to infinity of, make it real simple, x to the n. Okay. By the way, what's the interval of convergence for f of x? Very simple. You should be able to do it in your head, probably. Yeah, -1 to 1 and not including the endpoints. And let's suppose g of x, this is kind of tricky, but when you see it, it'll say, of course, as an example, n equals 0 to n to infinity. Of negative x to the n. What's the interval convergence of g? Not infinity. Multiplying by -1. The hint is it doesn't do much.
Does it just make it positive?
Yeah, the interval of convergence is still -1 to 1. Yeah, it doesn't change. Multiplying by a constant never changes unless you multiply by 0. But multiplying by a non-zero constant never changes the interval of convergence because you can pull that negative outside if you want. How about f plus g in terms of this way? What about the summation? Let me just do it this way. Of x to the n plus negative x to the n. What's the interval convergence of that? Or where does it converge, I think might be the better way of saying it. Any ideas? No. Here, let's plug in 0. 0 to the n plus negative 0 to the n. That's 0 minus 0. What's 0 minus 0? Right, it's 0. Plug in 1. Sorry, plug in n equals 0. Sorry. Plug in n equals 0. And you get x to the 0 minus x to the 0, which is 0. If you let n equals 1, you get x minus x, which is 0. If you let n equals 2, you get x squared minus x squared, which is 0. If you add 0 plus 0 plus 0 and keep going, what do you get? You get always 0. So this always converges. Doesn't matter what the x is. It doesn't even have an x when you simplify. So this has, this converges for all x. On the other hand, f and g don't. So you can gain convergence, but you can't lose convergence. And that's important to note. Any questions on that? Any questions? So you can gain but not lose. Okay, so that's number 1, and that's kind of a big thing to note, is that this is, it says it tells you where it converges, it does not tell you where it diverges. So it converges in I does not mean it doesn't converge outside I. It may or may not. Okay, number 2, and that is if you take kx to the m, an x to the n, then that's equal to kx to the m f of x. Okay, and it has the same interval of convergence no matter what the constant a is, and as long as m is greater than or equal to 0. So I want to remind you that this summation, maybe in this one I should write it out, n equals 0 or whatever you might be starting at to infinity. Might be worth it because we have an m and n. And the idea is you can pull out the kx to the m. That's all that means. It just means that you can pull it out. And that you're used to with sums is that if there is no n, you're allowed to pull it outside the sum. We've seen that before. Right? You probably saw it last quarter when you, in Bruce's class when you did integration. You can pull out constants. Anything without an n, you can pull out. Any questions on that? Okay, and the next one says, well, the summation an k x to the m to the n, that's equal to f of k x to the m. All that says is that you're allowed to do substitution. So remember, we have f of x equals this. So instead of x, if you put kx to the m, you can substitute kx to the m for the x, and it works. Okay, and then the rate and the convergence does not change. Okay, you actually stay convergent on I. Okay, you may get more. For example, if k is 0, it converges everywhere. But you never lose convergence by doing this. Any questions on this theorem? Any questions? Okay. So here's an example. I thought I'd give you one because I didn't give you this type last time, and I figured I should because it's an important example. And that is find the power series centered at x equals 2 for the function f of x equals 1 over x plus 1 over plus 2 over x plus 4. And what can we say about its convergence? Any questions on the question? All right, so now we have a function that's a sum of two functions. And if you look at the individual functions, do you all know how to at least have an idea how you might find the power series for 1 over x plus 1? Any thoughts on how you might find that? Ignore the second piece, just the first piece. And maybe 2 words. Yeah, geometric. So this looks like a geometric series. Okay, now we want it to be centered at x equals 2 and not at x equals 0. So we need to make that happen. So instead of x plus 1, I'm going to rewrite this as the following. I'm going to write 1, and then I'm going to say minus x, minus negative x. Oh, sorry, minus, and then we're going to have a negative x. Let's see, sorry, 1 minus, and then what? The key is we're going to have a negative. It's kind of tricky. And then we have an x plus 1. We don't want an x plus 1. We want an x minus 2 because we want it centered at x equals 2. Any questions on the goal here? If it's centered at x minus 2, we need an x minus 2, not an x. Okay, so I'm just going to blindly write down x minus 2. Any questions so far? All right, now that doesn't quite work because if I take 1 minus negative x minus 2, that's the same as 1 minus 2, that's the same as 1 minus 2, which is negative 1 plus x. So I need to add 2 to make it equate. So now if you simplify this, then we actually do get an x plus 1. I know I made it really messy compared to what it started at, but now I have the x minus 2, and I also have a 1 minus. Any questions so far? Then I'm going to do the same thing with the second one, or the same idea. I don't want an x plus 4. I want a 1 minus, And then I'm going to do a negative parenthesis x minus 2. And then I got to see how to adjust it. So 1 minus 2 is negative 1. I need 4. So I'm going to go plus 5. Anyone lost on what I just did so far? Tricky algebra.
Yeah, can you show us the step before, like before you added the, I guess, plus 2 and plus 5 to the denominator?
Okay, so I need to make it 1 minus r, right?
Uh-huh.
So I have a 1 minus.
Mm-hmm.
That's the
Yeah,
first
I
thing.
got
You
that
just
part.
blindly write 1 minus.
Okay.
Okay. Well, I have an x here.
Yes.
So I can't write it as 1 minus x because that'd be a negative x. So that's why I put the negative in front. Do you see that?
Yeah, I do.
And then I'm centered at x equals 2. So that means I have to have an x minus 2.
Mm-hmm.
So I'm putting all the things I need. And then at the very end, I decide what do I have to throw in there to make it equate.
Okay, I think I understand now. Thank you.
Yeah, it's very tricky, isn't it?
Yeah, it was a little confusing.
Yeah, but I'll let you know it's always the same trick when you're doing geometric power series.
Okay.
About centered at somewhere else. It's exactly the same thing. You always blindly write 1 minus parenthesis. If this is a plus x, then you make this a minus x. If this were, say, 4 minus x, then I wouldn't have to have a double negative. Do you see? Okay. And then you always say whatever the center is, you make that x minus the center. And then you figure out what you have to add to make it equate. It's always those steps in every situation with these power series. Tricky, very tricky. Okay, so I still have more to do. So let's do some more. This equals. And let's write down a fraction. Still have a 1 on the top for now. And then 1 plus 2 is 3. I hope you can all do that in your head. And then we have minus, parenthesis, negative, parenthesis, x minus 2. Starting to get a little prettier, isn't it? And then let's do the next one. Plus, fraction, 1 over. And then 1 plus 5 is 6. 6 minus parenthesis, negative, parenthesis, x minus 2. And the parenthesis. Okay, now we talked about this already, is when you have a 3 here, do you remember what I have to do? Remember how to do with that 3? I need it to be a 1, not a 3. Yeah, we divide by 3. I like to think about it as factor out the 3. Okay, so let's factor out the 3, and at the same time, I'm going to factor out the 6 for the second one. So that is equal to, and for factoring out a 3 on the bottom, really pulling out a 1/3. 1 over 3 times, and then we get 1 over, and then we have a 1, that was the whole point, minus, and then parenthesis, and then I'm going to have a negative x minus 2 over 3. Or how about negative 1/3 times x minus 2. Any questions on that? And then I do the same thing for the other one. I pull out, instead of a 3, I pull out a 6. So it gets messy. But, you're used to that. You wouldn't be in third quarter calculus if you couldn't handle messy math. So we got 1 over. And then we have a 1 minus. And then same idea, we're pulling out a 6. So we're going to have a parenthesis negative 1 over 6. And then we're going to have an x minus 2. Like so. Are we ready to turn this into a series? Have we done everything we needed to start writing down a series? Looks like you're all afraid to answer. Yeah, the answer is yes, we're there, okay? We've got it written as a geometric series form, kind of geometric series way of writing it, and we have the x minus 2. So now we can write down the summation. N equals 0 to infinity and then we still have the 1/3. Try as a fraction. One more time. 1/3. And now notice our r is negative 1/3 times x minus 2. So I can write that as negative 1/3 to the n, x minus 2 to the n. Okay, now technically it's negative 1/3 times x minus 2 all to the n, but you're always allowed to split those up. That's just basic algebra. Okay, and then we do something very similar. For the other one, you go plus and copy and paste and adjust. It's not 1/3, it's 1/6. Similarly, that was negative 1/6. And it looks like that. Any questions so far? And now I could put everything together. And I'm going to do that I'm going to do a few steps in one, so I don't have to keep typing all day. So that's equal to the summation, n equals 0 to infinity and I can write that. Notice both of these have a negative to the n, so I can write this as negative 1 to the n. And then we're going to have notice 1/3 times 1/3 to the n is 1/3 to the n plus 1. So times 1/3 to the n plus 1 and then plus, probably need one more parentheses, plus 1/6 to the n plus 1, same idea. In fact, I think I can copy and paste. Change the 1/3 to the 6. Close the parenthesis, and it's x to the n, x minus 2 to the n. Okay, and now I've written the power series centered at x equals 2 for this interesting function. So let me stop there a moment because I just did a tough example. Any questions on this tough example? I wanted to do one like this because I didn't do one where it was centered somewhere different with a binomial. Any questions on this? Okay, if there's no questions, let's get to the next piece. And that is multiplication. Addition was no big deal. You just put a plus. Okay, do you remember how to multiply two things? Let's say if I said, I don't know, x minus 3 times, how about y plus 5? Do you remember how to multiply that? If you say no, then you don't belong in this class. Just multiply it out, FOIL. Okay, what if we had something like, I don't know, x plus u, and then we had, how about y minus v? So x plus u minus 3, y minus v plus 5. Could you multiply that out? Do you know how to do that? Yeah. Okay. By the way, would you be smiling because it's so nice and simple to multiply this out? Or would you be like groaning a bit? Yeah, you'd probably groan a bit. Okay. On the other hand, how about this? How about x plus u minus a plus c minus w? And then how about y minus v plus 2q minus m plus, how about z? And I told you to multiply those out by hand. Do you think you'd just smile and say, oh, what a wonderful thing? Think you'd groan a little, or do you think you'd rebel? Yeah, you'd probably give up or rebel. Okay? Just to let you know, this is easy compared to what we got to do. How many terms are there in the power series we're looking at? There's an infinite number. Okay? So now we're talking about an infinite number of terms times an infinite number of terms. Okay? I think they call that hell. Okay? So if you're a really bad person and you die, you might be having to do that, right? Because it would take an eternity and none of it is fun. Okay? For most people at least. So it would be awful. So I want to let you know that multiplication of power series is hell. Okay, it is really horrible because it is like kind of like infinite FOIL. Okay, so here's what you can't do. So here's an example: summation n equals 0 to infinity of nx. I'll make it a 1. Sorry. Otherwise, it's just you can't go divided by n. Otherwise, of nx to the n times the summation n equals 1 to infinity of x to the n over n. All right. What you can't do is say, well, I'll just multiply these. Look, n over n is just 1. X to the n times x to the 2n. I mean, x to the n times x to the n is x to the 2n. So I get the summation n equals 1 to infinity of x to the 2n. Is that right? Absolutely not. Okay, you can't do that. Okay, and that is because when you're multiplying out these big long expressions, it's not just the first times the first plus the second times the second plus the third times the third. You have to do all the different combinations. Any questions on that? So you can't just say the n's cancel and the x to the n times x to the n is x to the 2n and I'm done. It's false. It's wrong. But here's what you can do. Okay, no matter how much you don't want to, we can write this written out. So if n equals 1, you get x, and then you get plus. If n equals 2, you get 2x squared. And then plus. If n equals 3, we get 3x cubed. And then plus. And then you get tired, so you put dot, dot, dot. And then we're going to multiply it. And we're going to do the same thing. If n equals 1, we get x. And then plus. If n equals 2, we get x over 2. We get x squared over 2. If n equals 3, we get plus x cubed over 3. And then we're tired, so I'm going to write plus, 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 dot, dot, dot. Do you all agree it's so far so good? I haven't cheated or done anything wrong? equals. Okay, now comes the interesting part. What I'm going to do is I'm going to do it up to the third power. And then I'll do plus dot, 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 and just like get lazy and pretend I knew the rest. So notice that what's the lowest order term? In other words, what power will be the lowest power when you multiply these out? Not x squared. Yeah, the lowest power you could get is just x times x. And there's only one way of getting x squared, and that is the first times the first. So that's just going to be x squared. Any questions on that? Now let's look at the x cubed. Well, how can I get an x cubed? I can take x times x squared, and I can take a 2x squared times an x. And that's the only way, those are the only ways I can get an x cubed. So what I'm going to get is I'll get 2 plus a half. X cubed. Any questions on how I got the x cubed term? All right, how about an x to the fourth? And the key thing is I don't actually need the x to the fourth term. I don't need this next term because then I'll get x to the fifth from it. But I can get an x to the fourth by taking x times x cubed over 3. So that's going to be 1/3. And then I can get a 2x squared times x squared over 2. Which is a 1 x to the fourth. And then I can get a 3 x cubed times x, and that's plus 3 x to the fourth. And then I should probably work that out. I get x squared. Oh, let me go plus dot, dot, dot. So I'm getting lazy here. So I get x squared. And then plus 2 plus a half is 5 halves. X cubed. And then plus, and a third plus 1 plus 3 is 13/3. X to the fourth plus dot, dot, dot. Any questions at all on this? Okay, how far could I go? Right? Okay, I can't go forever. I'd be dead before I was done. Yeah, as far as your heart desires, sounds about right. Okay. So to let you know that you can't go forever because we don't live that long. Can a computer go forever? You know, given what I just showed you, this is very algorithmic, which means that if you learn how to program, then you can learn how to make this happen. Okay. No, the answer, it can't go forever, but maybe it could go 100 terms. I couldn't go 100 terms because I just go crazy before that. But a computer tends not to go crazy, but its wheels spin after a while. Okay, but you could definitely do 100. So the point is, a computer can make this go really fast. Okay, you can go really high powers. Okay, a person would give up pretty quickly. Computers go a little longer before they give up. Okay. Now, again, you're not going to get an infinite because no one can do that, but we can multiply power series. Any questions on this example? Okay. So there's dividing also. Do you remember how to divide polynomials? Yeah, long division. Okay. Now, if you think multiplication is hell, I think long division, I think a division of power series is like for the truly worst evil people ever, like Hitler or someone. Hopefully is doing long division for the rest of eternity of power series. So the point is that there's nothing, it is so evil to try and do long division. So one way is doing long division. The other way is still really hard and miserable, but not quite as bad as long division. And that is saying that if we have an over bn, or summation of a n x to the n over b n x to the n, and we say, well, that's equal to something. We don't know what it is, but just call it c n x to the n. Then you can multiply by bn on both sides, and then you can do it recursively. Okay, so for example, if I have this one, if I want to find the power series for n equals 0 to infinity nx to the n over n equals 0 to infinity of 2 to the n x to the n, then what I do is say I don't know what it is, but I can always do this. I can write the summation. And instead of 2 to the n, we're going to have just cn x to the n. So we can always just say that's true. Then what I can do is I can multiply by the denominator. So let's do that. So I can multiply by the denominator. So let's get rid of that guy. And I can multiply it on both sides, like so. And then I can expand and write down that nx to the n is just, well, if n is 0, you just get 0. So if n is 1, we get an x plus, and n is 2 is 2x squared plus 3x cubed plus 4x to the fourth plus dot, 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 equals, and then we're going to plug in our n for the first one, and you get c naught, and then plus c1 x plus c2 x squared plus c3 x cubed plus dot, 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 and then times, now let's plug in again. If you plug in 0, you just get 1, and then plus, you plug in 1, you get 2x. If you plug in 1 again, if you plug in, 2, you get 4x squared. If you plug in 3, you get 8x cubed. Plus dot, dot, dot. Any questions so far? That first one should be not in. Okay, then you multiply and look. So notice here we get a c naught times 1 for the 0th order term. There is no 0th order, so c naught equals 0. Okay, then we get the first order term. Well, the first order term, c naught 0. So we get c1, just c1, and c1 must be 2. And then we look for c2. So we need this. So we know that c2 times 1, which is just c2, but then plus 2c1, which is 4. So c2 plus 4 must be equal to 3. So C2. So if C2 plus 4 is 3, C2 is -1. And then we just keep going. It's called recursive division. And we can get C3, C4, we can go as far as you want with a computer, especially. You can go hundreds. Any questions on this idea? Do you all agree this would be completely miserable by hand if I asked you to do, let's say, the 100th order? Nobody would want to do that. Do you all agree? Okay, you could look at it. Trust me, it's not fun. But to do the first few is not bad. And to program in a computer is not that bad either if you're experienced in programming. Okay, computers don't complain too much. It's a simple recursive for loop, basically. So if you don't know programming, hopefully you'll get there. Okay, the next thing is just a quickie. And if F and G are power series, and they both converge on I, and the product is written out as a C and X to the N, then the product also converges on I. So basically the same thing that we just said for sums and differences still work for products also. Any questions on, this is called the Cauchy product. Cauchy was like a main mathematician that wrote like hundreds and hundreds of important theorems. So one of those guys. All right, now I want to jump to the important piece and the main reason why we care. And that is derivatives and integrals. And the wonderful thing is it's easy. So the theorem is the derivative of an x to the n is just the power rule. It's a summation n an x to the n minus 1. But there's one subtle point here. Did anyone see it? It's not a typo. What's the subtle point? If you look at the two series. dx, that's not subtle. That's the whole point. This is how you take a derivative. There's one subtle point that I didn't say, but it's here written out. Yeah, n equals 0 and n equals 1. And that does change. And the reason why you have to do that is if we put n equals 0, we're going to get a negative exponent. And that's not what happens when you take derivatives. You don't get negative exponents. So kind of an important thing to note is when you take a derivative, you start at the next number. If you took a second derivative, you start at n equals 2, by the way. So that's important to note. Okay, and then same thing, the integral of a summation n equals 0 to infinity, an x to the n dx, is just the power rule. So summation n equals 0 to infinity of an over n plus 1, x to the n plus 1. And then hopefully you're all used to plus c. Any questions on taking an integral and a derivative in terms of the formulas? Does it look easy? And the answer is, look easy or not? Yeah, so with integration, there's no issue. Yeah, so it should look easy. Okay, if you compare this to what you had to do last quarter with integrals, where you had a whole bunch of different rules for integration, this is it. This is all you ever need to know about integrals when it comes to power series. You can integrate anything. Isn't that beautiful? Okay, and derivatives, they're a little messy, not too bad. Integrals are brutal, but not with power series. They're wonderful. Okay, and then a note, the radius of convergence is the same for the original series as it is for the derivative and the integral. So the radius of convergence does not change. On the other hand, for the derivative, okay, the interval of convergence can change, and also for the integral. For the derivative, okay, if the endpoints don't converge for the original, then the derivative endpoints don't converge, but not vice versa. Okay, so in other words, you could have a series that converges at the endpoints, take a derivative, and now it doesn't converge at the endpoints. And integrals are the opposite. So you can actually gain an endpoint with an integral. You could start out with a series that doesn't converge at an endpoint, take an integral, and now it does. Okay, so that's important. Okay, but you can't lose an endpoint for convergence. So that's important to note. Let's look at examples, because that's the whole purpose. Okay, so here's an example. D over dx, n equals 0 to infinity of n minus 1.5 over n squared plus 2n plus 3 x to the n. All right, does this look kind of messy? It looks messy. It's not. It's clean and easy, and you should smile when you see something like this, especially if you have a computer, because I'm just going to copy and paste. Put an equal sign, get rid of the derivative. Oops. And then what has to change? How do I take a derivative of x to the n? What's the derivative of just the x to the n part? Not integral, derivative. What's the derivative of x to the n? It's even easier to type. So what's the derivative of x to the n? And x to the n minus 1. So I just say n x to the n minus 1. And then one more little thing I have to change, and what is that? N equals 1. I'm done. Okay, notice that whole n minus 1.5 over n squared plus 2n plus 3, that's a constant, right? We're doing d over dx. There's no x there. That's why this is so easy. Do you all agree that was really easy? Okay, there's nothing to it. Derivatives are so simple. You can take a derivative of anything. Okay, and I want to let you know, it's a little too advanced for this class, but I want to give you a kind of a heads up on the main purpose of all this. And that is, if you have a differential equation, I don't know if you remember differential equations from last quarter. You got some, hopefully from Bruce. Did you? Yeah, hopefully you know that. And I don't know if he told you. Do you know that without power series, most differential equations cannot be solved, but power series makes them all solvable. So it means every differential equation can be solved using power series. Okay, it's a little beyond what we're going to be doing, but I will let you know they can all be solved. So let me give you an example, a science example. Have you heard of the Schrödinger equation? Have you heard of that? Yeah, you've probably heard of it. You probably couldn't tell me exactly what it is. But I'll let you know the Schrödinger equation for hydrogen has been solved, and they have a solution to it, no problem. And then as soon as you jump away from hydrogen and go to helium, or God forbid, uranium or something, good luck. Okay, it's not solvable in regular ways of solving. So what you do is you do a power series. And then there's going to be all kinds of multiplications and stuff. So you do as many terms as you feel like it, maybe 100 terms with a computer. And then you can solve the Schrödinger equation up to a very good amount of accuracy using power series, because derivatives are so easy. Okay, there's going to be multiplication of these power series in the Schrodinger equation. And I'll let you know that it's a pain, but computers can do it. You know, we can do it by hand for a few terms. So there's a major, major application of this, and that's the biggest one. And that is solving differential equations. Okay, but we can do integrals too. How about the integral? N equals 0 to infinity of 1 over n plus 1, x to the n. I bet you can do that. See if you can try it. And the key is, of course, you can't do this because you're not at my computer, but you can copy paste, or I can copy and paste. And I'll let you change a few things. Yeah, we're going to have an x to the n plus 1. And we're going to have an n plus 1 times n plus 1 on the bottom. So that's an n plus 1 squared. But actually, that's not it. There's one more piece. Now, n equals 0 is correct. There's a different piece. Here's a hint. If you were in my class, I don't know what Bruce is, but yeah, you lose a point if you don't do this. That is right, plus C. I call it the 1 point C. Any questions on that integral? Okay, let's look at this next integral. The integral of 1 over 1 plus x to the 7th. Did you learn how to do this last quarter?
It looks very familiar.
Really? No. My guess is you didn't learn how to do this. Okay. This is there actually is a possible way of doing it. It is absolutely horribly brutal. Okay. You have to factor this under complex numbers, then factor this and then do partial fractions of 7th order. Okay. If you ever did anything like that in Bruce's class, I got to talk to Bruce because he's just was in a bad mood or something. Okay. So if you think you did this, I don't know. Okay. This is a completely miserable problem. On the other hand, now that we have a new tool, it's actually not that hard. I see a 1 over 1 plus x to the 7th. How do I rewrite that in this class? Yeah, it's a geometric power series, and it's not that hard. Summation n equals 0 to infinity. And then we can rewrite that. I'm going to just say it. 1 over 1 minus negative x to the 7th. So we get negative x to the 7th to the n, still dx. That's equal to the integral of the summation n equals 0 to infinity. And I can rewrite this as negative 1 to the n times x to the 7n, just using the rule of exponents, dx. And the whole idea is I can take that integral and put it through and integrate. And that gives me summation n equals 0 to infinity and negative 1 to the n. And now we get an x to the 7n plus 1 over n plus 1. And then plus c. Was that hard, by the way? I'm done. I've got my integral. So if you compare that to trying to do it using partial fractions with a 7th order thing that you have to factor out in a miserable way. Isn't this beautiful? Okay. The bad news is if I said, all right, now plug in x equals 4, then it's not so easy because you got this big series. Okay. Or say n equals a half. Okay. 4 doesn't work. The radius convergence here is 1, by the way. How about the inverse tangent of x? How would we do that? Any thoughts? Any thoughts how I might be able to integrate the inverse tangent of x? Again, it's one of those that Bruce might have shown you. It's pretty brutal, though. ln, there might, I mean, with the brutal way, there's some ln's. But here's the nice thing. Hopefully remember the inverse tangent of x is the derivative. We know the derivative of the inverse tangent of x is 1/1 plus x squared. So the inverse tangent of x is the integral of 1/1 plus x squared. Do you all remember that from last quarter? I'll just write dx and then another dx. Basically integrate twice. But check it out. 1/1 plus x squared is an easy one for power series. So that's, I'm going to write integral. And then we can have a summation. N equals 0 to infinity. And this becomes a -1 to the n, x to the 2n. Okay. Any questions so far? Okay, there is a plus c here. And then note that if we have this, well, we actually, there's not a plus c until we integrate. So now we're going to integrate. So that's equal to, I think the easiest is copy and paste without one of the integrals. It's going to be the integral of summation n equals 0 to infinity, -1. That shouldn't be 2, it should be n. -1 to the n, x to the 2n plus 1. Over n plus 1, over to 2n plus 1. Now, technically, there's a plus c, but we know that the inverse tangent of 0 is 0. So that means that c is 0, so we're okay for the first plus c. Second one, we're going to get a plus c out of it. Then we say that's equal to, and now we just integrate again. And remember, the n stuff is just constants. Oops, not yet. There we go. Now we integrate again. So we're going to have a 2n plus 1 times 2n plus 2. And that's going to be an x to the 2n plus 2. And then plus c. And now we've integrated the inverse tangent of x. A little tricky, but if you know the trick, it's actually quite easy, right? All I needed was the power rule for integrals. That's all you ever need to do power series with integrals and derivatives. So I'm out of time. So let me stop the share and stop the recording.